Hello and welcome back to Calculus 1. We are going to take a look at derivatives, the detailed look at derivatives of exponential and logarithmic functions and learn the most powerful differentiation technique that there is. So there are like three parts of this lecture. The first part, exponential derivatives, and then derivatives of logarithmic functions, and then part 3, logarithmic differentiation. So that's that technique that I mentioned. So the first part is derivatives of exponential functions. So we start with what we already know. You already know that the derivative of e to the x is e to the x. You also know that the derivative of e to the ax is ae to the ax. And you also know, because you learned chain rule last class, that the derivative of e to the f of x, which is a function of some sort, is going to be e to the f of x times f prime of x. So all of these formulas you know from before on some level, right? And technically, the one formula that you would be using most of the time is this formula here. And throughout your calculus and engineering education, that is the formula that you would see pretty much all the time. There is one formula that is more general, right, that is general case, which is like the higher tier than e to the f of x, and that would be b to f of x, meaning you can have any base other than e. You can have 2 to the sine x, you can have 5 to the whatever, x squared plus 7. So, see, when you write e is a particular number, right? We know that what e is. So, all three formulas are stuck with e. The general case for exponential differentiation is when you allow e to be any number. So the boss of all exponential functions, derivatives, is this one. Any number in a base, any function in the exponent. So you can't go more general than that. But as I said, you are not going to run into too many problems, obviously, when we craft them in mathematics, so you can do your mathematical gymnastics with it. But in later applications and so on, for your engineering courses that are coming up and stuff like that, you will always be using the one on top, e to the f of x. So what is this one? This one is going to be b to the f of x times f prime of x times ln b. So that is the general exponential formula. But I'll say over here, most of the problems use this. So that's the one on the bottom is the boss of all equations, but the one in the middle, right, the one with the e to the f of x, is the one that you will be using in 98% of the cases. Electrical engineering, mechanical courses, some stuff in chemistry, and physics, obviously, right? So they all use that particular formula. So that's that. I'll write here general case. And as I said, general case you're going to see on your homework and your lab and possibly your exams, but it's extremely rare to run into that one outside of the classroom setting. The one on top, everywhere. Now, it's important to see that the formula on the bottom actually contains all of the formulas above. That's why it's called general case. Because if you realize, for instance, that your b is equal to e, and your f of x is equal to ax, you will quickly derive this formula here, just by plugging these things on the right side. So let's try that. Let me move the f of x over here. So what happens? Your b is e, your ax is exponent, times the derivative of ax is a, and then your ln of e, which is equal to 1. So there's your 1 times a, and you get a e to the x. I mean, this obviously has to happen because all three formulas above are a part of the bigger formula on the bottom. And this is the rule in mathematics. You keep upgrading, getting more general, generalize. In linear algebra, you get to write your entire Calculus 1, Calculus 2, and Calculus 3 in one formula. It's like cool. It's really cool. I know, right? So as an example, what is the derivative of 5 raised to the tangent x? Well, your b is 5, your f of x is tangent, so you just write out the right-hand side. It's going to be 5 tangent x times the derivative of tangent is secant squared, very good, x times ln 5. And problem done. So you for this particular case, you either know the formula or you don't. You can't make this thing up. You can't make it up. So d dx of what? D dx of 6 x squared minus sine x. So your f of x is x squared minus sine x, and your b is 6. So it goes copy the same thing times the derivative of the exponent, which is 2x minus cosine x, times ln of the base times ln 6, and you're done. So exponential derivatives are absolutely the easiest thing that you can get, because they are structured as whatever your problem is, you copy the same thing, you take the derivative of the exponent and you multiply by ln of the base. If that base is e, ln of e is 1, so you don't have that last component. It collapses onto the formula above, and then it goes from there. So that's part 1 of the lecture. And the second one is going to be easy too. The derivatives of ln, because ln x is the inverse function of e to dx. So if e to dx was easy, then its inverse, ln, should be easy as well. So to now take a look at derivative of log functions. First, we take a look at First, we realize that there is a conversion that exponential functions and logarithmic functions are inverses of each other. So here in orange, I'm going to say a raised to the b equals c converts into log base a of c is b. So that's the conversion. And we all understand that log base e of x is ln x. So ln x is just a lazy notation for log with a base e. So all of the important functions for engineering and well, technically every walk of life, if you paid attention in your pre-Calculus 1 class when you did those word problems, you found problems that did compound interest, which is obviously business, money. Then you found carbon dating, which is all about history. Then you found radioactive nuclear decay, garbage decay, which is environmental sciences. Then you found problems with metabolizing medication in the bloodstream because each medication has biological half-life. I use sometimes on my exams biological half-life of aspirin and Advil. Advil is 1.9 hours, which is why you get to take Advil every 4 hours. So these things, right? So that's medical application, and then clearly you have engineering. If you want to charge, discharge capacitors or batteries, it's going to be exponential and so on. So exponential function, the e to the something, it shows up in all walks of our life, like everywhere. And you can also paint e, so there is e in arts as well. You have every single aspect of our human dealing has exponential function e to the x in some form somewhere. Yeah, well, e to the f of x somewhere. So if the exponential part is going to be e to the something all the time, then the logarithmic inverse part is always going to have e in the base, which means it's ln. So that's the reason why ln is everywhere. It's because it's the inverse of the function e to the x, which is everywhere. And as I said, if you paid attention in your pre-calc 1 class and you did those word problems, which is clearly the most important part of the entire course, you would know that. So now, when you take a look at ln x as a notation, it's just a notation. It's a lazy notation. It's literally 2 letters shorter than to write this. This one has 5, 1, 2, 3, 4, 5, and this one has 1, 2, 3. That's all it is. It's nothing special. It is using all of the same rules as log. It's just shorter notation, and then n stands for natural, so we say natural log, where the other one we just say log. So 2 bases that you use in sciences, you will be using base 10, and you will be using base e. Now, base e, I said it's everywhere. Base 10 is not as frequent at all. Chemistry calculations for pH and some other things would have log base 10. In physics, if you're dealing with earthquakes and sound waves and sound intensity and so on, you will have log base 10 again. So earthquake, Richter scale, and so on, that's the intensity of the earthquake is, the magnitude is measured in increments of 10 times as bad as the previous one. So the earthquake on Richter scale 7 is 10 times more devastating than 6. And 6 is 10 times more devastating than 5. And 5, so it goes in the times 10. So when there is an earthquake that it's 8 or 9, it just leaves the flat plane behind. When you have a 5, it leaves just a lot of scared people and some things crumbled and fall off the shelves, right? So it's a huge difference when you go 1 point. Currently, you are experiencing 1. at all times. But we evolved on this planet for the last 100,000 years, so we tuned that out. If you go to a machine that measures tremor, there is always that little line the little ink hand that draws that little line that goes up and down, up and down, up and down. The Earth's crust that we live on is because Earth is spinning very fast, about 14,000 miles per hour. That's how fast the Earth is spinning in space, in place, and then it goes also around the sun, and then the whole solar system. So we're going in a spiral like this. When the galaxy turns around, it's just the amount of motion that is happening, right? We don't perceive any of it, obviously. If Earth is to stop spinning, there was that first Superman movie from 80s or 70s, maybe 70s, I don't know when, the first Superman movie. At the end of the movie, Superman flies around the Earth to stop it, and then flies the other way to spin it the other way, so that the events can be undone, so Lois Lane comes back from the dead, because he didn't get it in time to save her, and then he spins the Earth the other way around again. If you stop the Earth from spinning, if the Earth stops, everything on the surface will continue moving 14,000 miles per hour, So, yeah, that's not such a good idea, but it's fine, it's moving. So, we have two bases, which is why all of your calculators only have capital Log, which calculates logs with base 10, and then you have capital Ln button that calculates base e. And you don't have log base 2 and log base 7 because we don't use those in any of our science and physics applications. So those of you into chemistry and bio, eventually when you run into the formulas for pH, you are going to do log base 10 calculations. Those of you going into engineering and everything else, you will have base C, and then base 10 for waves and earthquakes and things like that. So now that we understand this little piece, we go and we say that the derivative of ln x, right? So the derivative of ln x is simply 1 over x. So this is the first basic formula. But then again, you are usually don't have just ln x. In most cases, you are going to have ln of some function. So ln of f of x. So ln of x squared, ln of sine x, ln of something else. And now the formula is, this f of x is called the argument. So it's f prime over f. It is so damn easy. You see the function that it's inside ln. Guys, Control C, Control V, and then take the derivative, okay? That's all it is. Control C, Control V, and then take the derivative. If you're using Mac, I think they have something also for that. Can Macs cut and paste? Do they have that function?
Yeah.
They can? Okay, good. Glad they developed to that point. So this formula is the one that you would be using 98% of the time. So this is that we do have the boss formula. Remember that the boss formula allows for any base, so that we can flex in mathematics and show off our math skills, right? But the one for practical purposes, your engineering courses and most of the math stuff you do is going to be right here. So this is the one. We use this formula most of the time. So if you are picking out of all formulas which one to memorize, this one will be your greatest return at 90+%, right? The general one that I'm going to write now, you are only going to see this on your math exams and labs. So this one is the derivative of log base b of f of x. So we know that for ln, so far we know that for ln, you have the what do you call it? Base e, right? That's the one. All right. So what is this one? It's going to be the same thing with functions, except now you're also going to have ln b, and it goes in denominator this time. So it's f prime over f, and then you have your ln b in denominator. So this is general case. But we don't, as I say, use this much outside of our mathematics. So now, let's go with the example, the derivative of, let's first do the most important formula. What's the derivative of, let's say, x squared minus square root of x? Well, you take this x squared minus root x as is, and you just copy it in denominator. So that's what I say, Control C, Control V. And then you take its derivative and place it in the numerator, which is 2x minus 1 over 2 root x. Hopefully you memorized by now that the derivative of root x is 1 over 2 root x. You can always go and figure it out by writing x to the 1/2, and then you do the power thingy, right? Drop the half. That's always available to you. But you can also memorize, just because you are going to see this derivative of square root of x many, many times. So you just want to do yourself a favor and get rid of it. I mean, you can also do the limit. All right. We are not happy with the double fraction, right? So we are going to multiply top and bottom by 2 root x to get rid of the denominator, and that will help us. So we have 4x root x minus 1 divided by 2x squared root x minus 2x. Now you can see that you can factor out, you don't have to, because you can't cancel because of minus 1. You can factor out 2x in denominator, but who cares? All right, that's good enough. So this is the one. You can also have trig inside. So what's the derivative of ln of, let's say, tangent x? Derivative of ln tangent of x. So you put tangent as is in denominator, and the derivative of tangent is secant squared x goes on top. And you can simplify this a little bit. The secant is going to be 1 over cosine squared x, and the tangent is sine x over cosine x. So one of these cosines dies, and the problem is 1 over sine x cosine x, which you can just further write as secant x cosecant x, because you can split this into two fractions, 1 over sine and 1 over cosine. 1 over sine is cosecant, 1 over sine. 1 over sine is cosecant, 1 over cosine is secant. So you could just have this as a result. So that's a little bit of trig. And now the general case, the boss formula. What is the derivative of log base 3 of, let's say, x squared minus 7? We have exactly the same as before. We have copy and paste in denominator, its derivative on top. So as you can see, it starts exactly the same. The only thing that you have to do new, because you have base 3, is to multiply in denominator ln 3. So that's the only new thing. And we're done. Just walk away. d dx of log of, I don't know, 8. And then the function is what? Let's go with x. No. How about if we put sine squared x? So we introduce the annoyance of a chain rule within this one. So we know that we are going to copy sine squared x in the denominator, and we need ln 8 in denominator, and we need the derivative of sine squared x on top. That will be 2 sine x times the derivative of the inside, which is sine cosine x. So now one of the sines cancels, and what's cosine over sine? Cotangent. So we have 2 cotangent x divided by ln 8. ln 8 is a number. I can fit this here. Cotangent 2 cotangent x divided by ln 8. And that takes care of that. So these are the basic exponential and logarithmic derivatives. And now it's time for us to see the most powerful differentiation technique ever. So what is that differentiation technique all about? Remember when we did the chain rule and product rule and quotient rule, and we started mixing those, and the problems were really long and annoying and difficult to work with? Now I'm going to sound like Morpheus from Matrix. What if I told you, right, that you can take all of those derivatives mentally without writing anything down? It doesn't matter how complicated they are. How about if every single derivative we did so far in this course, you can just look at it and just say the answer. And not just give the answer, but give the answer in a factored form. Actually, what you're doing is just taking the entire chapter 3 and saying, why did I spend 3 weeks on this if I could have just learned this first on the first shot and be done? Well, see, the trick is that behind logarithmic differentiation, all of the steps of what we did so far, they're in it. So it's like this great culmination of everything that we did. So if you look at the problem, the derivative of, and now you have something really crazy. Let's say you have x cubed minus 6 raised to the 5th power times the 4th root of, I don't know, sine x. And then now all of this divided by x squared cotangent 3x. This would be a living nightmare to do conventional methods, right? Because what you have there is a quotient rule problem, right? But if you take a look, both numerator and denominator have product rules each, and then each one of these terms is a chain rule, right? So you have what? You have 3 chain rules, 2 products, and a quotient. And what I am arguing that with sufficient practice, you would be able to just say the answer without writing anything down. I'm not talking 1-step or 2-step calculation, nothing. You just say the answer. And it's in a factored form already. This is how crazy this differentiation technique is if you practice it. Now, I always have in each class a student who is so fascinated by this, like I was, and practices this so much, and that student earns the title of the designated derivative taker. Right? So, and the coolest thing about that is that you get to move on to Calc 2 or Calc 3, and then as the functions are written on the board, you are dictating derivative along, like the answer, and everyone else is like, what the hell is going on? so yeah, you can get to those things, right? So let's go and discover logarithmic differentiation, and then we're going to come back to something like this and just do it like nothing, right? So what I'm going to do is, you wrote this problem down, right? Because I'm going to erase it, and then you will tell me later, I just put anything up, it doesn't matter. You can go home and make your problems, and yeah. So the title is Logarithmic Differentiation. There we go. This is on page 214 in your textbook, and they don't give it so much, you know, hype as I do, but when I saw this as a student, I said all my derivative problems are solved now. So what is this all about? Well, first off, we need to review the formulas from pre-calculus which decompose logarithmic functions. You had 3 formulas for sum, difference, and the exponent, and they go like this: ln of x times y is ln x plus ln y. ln of x over y is ln x minus ln y. And the last one, ln of x to the power p is p ln x. So these are your 3 formulas which were presented in Pre-Calc 1, and they were used in Pre-Calc 1 to condense multiple logs into a single log so that you can solve logarithmic equations. And you did very few problems of expansion because you had no use for it in pre-calc. Now the tables are turned. We don't care about compression. We only worry about expanding expressions. What I want to expand, so this is your review from pre-calculus. I want to expand ln of x squared times 4th root of x divided by x squared plus 1. Right? I want to expand something like this so that each individual term has its own ln. Now you remember how easy it was to differentiate ln, right? You copy the function on the bottom and you just put its derivative on top. That's the key that you can do it mentally, actually. Because what's the derivative of x squared? 2x. What's the derivative of x to the 1/4? X to the negative 3. And what's the derivative of x squared plus 1? It's 2x. So it's a joke. right? But you don't even have to worry about those exponents, actually, because by the rule number 3, they jump in front. Exactly. So this becomes like nothing. You already see it, but it becomes nothing. So this is going to be our ln of x squared plus ln of 4th root of x minus ln, can't fit there, ln x squared plus ln of 4th root of x minus ln of x squared plus 1. And now, using the rule 3, we can kick out exponents in front. So this becomes 2 ln x plus 1/4 ln x minus, this one cannot be broken because it's addition, so it has to stay, the last one. If you are able to do this mentally, right, after some practice, which is pre-calc 1, taking any derivative of, right, it doesn't matter. If you ever heard in martial arts, certain martial arts claim that, you know, the more opponents you have, the easier it is to fight them. This is that equivalent, okay? You just need to know some stuff. So let's go and work out a problem. So say we want to differentiate, and we'll do, right, this easy example. Now, hopefully you immediately would agree with me that this would be a living nightmare to do with a conventional method, because you have a quotient rule problem with a product rule on top and then some chain rules floating about. So not that fun, right? So this is the way that we deal with it, and then eventually we will be able to see the shortcut. So we say y equals, leave some space, x squared 4th root of x over x squared plus 1, and then we ln both sides. On the left hand side we have ln y. On the right hand side we have the expansion of this, which is 2 ln x plus 1/4 ln x minus ln of x squared plus 1. That's the same one, because I'm using the same function as above, so we expand. Expand. And once you expand, you hit this with the derivative. So this is the mathematics that is happening in the background. You will not be doing this. So 1 over y dy dx, it's a chain rule, right? You took the derivative of y in respect to x, so there is a chain dy dx, is equal to, the derivative on the right hand side is a joke, right? It's 2 times 1 over x plus 1/4 times 1 over x minus, remember, copy the function as is in the bottom and then take its derivative on top. Now, this y goes to the other side, but we know that the y is our original function. So dy dx is equal to y, which is x squared 4th root of x divided by x squared plus 1, times 2 over x plus 1 over 4x minus 2x over x squared plus 1. Oh, yay, that's factored. Right? But it's in a factored form. There's nothing else that you can factor out from the entire problem. Now, the question is, now, I would encourage you to, when you get home, because our class, we only have 3 hours here, right, left. When you get home, and you have more than 3 hours, do it the regular way. See if you can factor it into this, right, and good luck. All right? So 4 lines. 1, 2, 3, 4, and we got this. Now, what I am arguing for is that you should be able to write this just by looking at the problem without writing anything. Why? Because the pattern is, I shouldn't say, but I will, pattern is very easy. The derivative of any of these complicated forms is going to be, first, copy the same thing. Because you will always have the ln y and 1 over y, and y will always go on this side. So every solution will always start by copying the original problem. And then in this bracket is the derivative of the expansion. Every inner exponent is a coefficient which multiplies, so there's your 2 1/4. And whatever is left within the ln is the thing that goes on the bottom and its derivative on top. So when I see x squared, I know that 2 is the coefficient that is in front of ln, x goes on the bottom and its derivative 1 on top. There it is, 1 over x. Over here I have a quarter, I still have an x, so 1/4 times ln x is 1 over x and a quarter, so 1 over 4x. Just by looking. This thing is in denominator, therefore minus. This goes in denominator of the fraction and 2x on top, because derivative of, so if you just mentally are keeping track, this goes in front, derivative of x is 1 on top, great, this goes in front, 1/4, x goes in denominator 1 on top, 2x squared plus 1, 2x on top, in denominator, so it's minus. It is a pattern that you can learn, practice, 10, 15 problems, and it becomes very quick. At that point on, you go back to any problem that we did in class, and you should be able to get the derivative like this just by looking at it. And it's really, really cool thing. Now, obviously, if you don't know expansion formulas for ln, if you don't know what the individual derivatives are of x and stuff like that, then clearly it's not going to work. Let's take a look at another example. Say the function you want to take the derivative of is sine cubed x times x squared plus 6 to the 8th power divided by the square root of x minus 1. You can do this step by step, put ln each side, expand, and when you do all of those things, you get the answer. So we ln both sides, and we have now ln y is equal to, and now you have to expand this. Remember, every exponent is going in front of ln. You know what? I want to add one thing. I want to add x to the 4th in denominator for one reason, and we'll see why. So add x to the 4th in denominator in front of the square root. All right, let's go. So this is going to be 3 ln sine x plus 8 ln x squared plus 6 minus 4 ln x, and here is the grade killer. Ready? Minus 1/2 ln of x minus 1. I understand that you see a product between x to the 4th and the square root, but it's still in denominator, so it's a minus, because this expression on top with a sign is divided by x to the 4th, and it's also divided by the square root, which is why both of those terms that are in denominator have minus each. All right? So usually that's where your grade plummets, right? It's algebra. So both of those terms have to be negative because they're in the denominator. So when you're doing the expansion, whatever is in the numerator is a positive ln, and everything that is in the denominator is a negative ln because it's divided by. Now we take the derivative and we can just write the answer, right? dy dx is, copy the function as is, so sine cubed x, x squared plus 6 to the 8, divided by x to the 4th square root of x minus 1. And now, in parenthesis or bracket, whatever you want to call it, we have 3, put sine x in denominator, its derivative cosine x on top, plus 8, x squared plus 6, right? Control C, Control V, 2x on top, minus 4 times 1 over x, minus 1/2, Control C, Control V, so x minus 1, and then 1 on top, and now you just fix it. Now you can do any of these, and it doesn't matter how complicated they are, because you're always taking derivatives of a basic ln. And that's, you always copy the function on the bottom and its derivative on top, and you keep moving to the next, to the next. So this is going to be 3 cotangent x plus 16x over x squared plus 6 minus 4 over x minus 1 over 2 open parenthesis x minus 1 and then close bracket, and that's it. It's in a factored form, ready for you to say, hello, chapter 4 equal to 0, and then, well, clearly it's way too crazy for something like that, but if you are to find zeros, So are we ready for the problem that I gave at the beginning? What was that one? Y equals something.
X cubed minus 6, all that to the 5th power.
Okay.
And then the 4th root of sine x.
Sine x.
Over x squared cotangent 3x.
Cotangent 3x, not cube, right? It's 3. Okay, good. So we expand this, so ln y is equal to 5 ln of x cubed minus 6 plus 1/4 ln of sine x minus 2 ln x minus ln of cotangent 3x. So now the derivative dy dx is equal to copy the original function and just now take derivatives of each one of these separately, but they're all basic ln's. So we copy x cubed minus 6 in denominator. The derivative of that is 3x squared times 5, 15x squared, plus 1/4 copy sine x in denominator, its derivative cosine x on top, minus 2 over x, because derivative of ln x is 1 over x, and then minus copy cotangent 3x in denominator. And what is the derivative of cotangent? Negative 3 cosecant squared 3x. Very good. We have to get that negative there because it's a negative 3, because it was a 3x. And there you have it. That's the derivative. You can fix this term by writing a cotangent in, and you can cancel the trig and put the plus there, right? So you can dress it up a little bit more. But come on, right? Doing this, right? Position 2, a quotient rule which contains 2 products and 3 chains. Come on. Right? There's no contest here. There's no contest at all. This technique is insanely powerful. And as you become better at it, you will be able to actually just write out this final answer by looking at the problem without that intermediate step. So your ability to decompose these log functions, right, might be shaky now, which is why I'm writing that middle step. But if obviously I'm to take this derivative, I would go immediately to the last step because expansion doesn't bother me. So practice and you will be there. You will be there if you want to be there. Otherwise, it's just like -6 or something on a test, like once in a lifetime. Who cares? Just don't worry about it, right? All right, good. That's the lecture. We're done. Exponential, logarithmic, and logarithmic differentiation. Three parts. Bye.